So today we're very excited to have with us Dr. Adriaan Duivenvoorden, probably pronounced that wrong badly, but he was previously at Princeton and now is a Flatiron Research Fellow at the Center for Computational Astrophysics at the Flatiron Institute in New York. And Adriaan is an expert in CMB mapmaking and analysis, and has been really instrumental in the Atacama Cosmology Telescope in the mapmaking and analysis, and also is heavily preparing for the Simons Observatory, which is an upcoming CMB telescope. So without further ado, please take it away.
Thank you, and thanks for the invitation. So yeah, I will talk about the Atacama Cosmology Telescope. I'll mention mention something about the telescope, then I'll say something about their upcoming data release. I'll mention our recent results on CMB lensing, and then I'll go on to talk a bit about the title of my talk, trying to make use of the maps that we create themselves, so going sort of beyond the usual thing we do, which is taking just the power spectrum of the map and looking at that, but sort of try to interest you in the other things we can do with these maps. But so first about the Atacama Cosmology Telescope, here you see it on top of the mountain in northern Chile. Unfortunately, the telescope is now being decommissioned. It had a great run, but although the telescope is now gone, the collaboration is still very much alive, and there are still lots of interesting science we can do with the data, and we're still working through it. So, brief summary about the telescope. Like I said, it's on this mountain in northern Chile. Chile is nice because you get access to quite a lot of the sky, and we make use of that by mapping something like 40% of the sky, which is quite a lot for a ground-based survey. And the other notable thing about ACT is that for at least CMB standards, it's a fairly large telescope. It's a 6 meter diameter telescope. If you compare that to, for example, the Planck CMB satellite, very important CMB data set, we have something like 5 times the resolution. So that's quite a big increase. Okay, timeline. So I said ACT something like 2007, 2022. Along the way, the telescope, or really the camera, was upgraded several times. So started off with this camera called MBAC, then went to ACT-POL, and then finally Advanced ACT. And along the way, we also went from observing relatively small patches of the sky to looking at this something like 40% patch of the sky. And in these different blocks, you see the different detector arrays, so essentially different pieces of the camera. They all have a name, PA 1, 2, 3, 4, 5, 6, 7. What it's also shown is the frequencies in which they observe. So along its lifetime, ACT observed from it's observed in 30, 40, 90, 150, 220, and 280 gigahertz. Not all at the same time, but sort of span that frequency range. So for now, I want to focus on the sort of modern data that ACT has fairly recently taken, so from something like 2017 to last year, with this advanced ACT camera. 3 of these detector arrays observing in 90, 150, and 220 gigahertz over this fairly large patch of the sky. And we call this data set DR6, so data release 6. It's not out yet completely, but this is going to be what we're working on now, and will be out relatively soon. Just to give you an idea of how this DR6 release will improve over previous ACT releases that you might be familiar with. Here's a plot that shows you on the y-axis the map depth, which is just a measurement of the noise standard deviation per pixel, or really per arc minute, in polarization. And the way this plot works is you look for a certain map depth, and then you can read off how much area of the sky do we have that is at that depth or better. This horizontal gray line here is again this Planck satellite that I mentioned before, and then the 3 colors are the 3 ACT data releases. So ACT DR4 is most of the ACT pole data. And you can see there we were not observing this wide region. We're mostly focusing on these smaller patches of sky. And you see on these smaller patches we're doing much better than Planck, but it's again a relatively small patch of the sky. Then ACT DR5 was a sort of intermediate data release where we took some of this advanced ACT data, which again is over this large patch of sky. You see that we're really starting to beat down the noise over a larger patch of sky. And then this upcoming data at DR6 is where we combine all of this advanced ACT data, and you see that we're really over this 40% of the sky are significantly better than this Planck data, which is very exciting for the type of science you want to do. So this DR6 map not available, as I said, but if you want to get a taste for that, you can look at this DR5 data set, and this is how it looks. This has been combined with Planck, but it shows you the sort of the patch of the sky that we observed. ACT, like I said, this is very high resolution, so really a plot like this is not so indicative of what we actually have. So if we zoom in on a small square there, and plot that, you see more what the data actually looks like and what it enables us to do. So here at the top is the temperature data, so the total intensity data. In the background, you see the primary CMB. And then on top of that, you see all these red and blue points, which are either dusty galaxies or even galaxy clusters. The blue ones in this case are the galaxy clusters. And in the bottom, you see the one component of the polarization field. And the cool thing is, if you're a CMB scientist now, at least you look at this and you realize this is not noise anymore. This is now also all signal dominated scale. So we're really getting this very pristine view of the polarization of the instrument, of the CMB, which is where a lot of the improvements will come from. Here's a sort of a plot trying to illustrate that. So this EE and TE, which are the power spectra of the polarization, and the cross spectrum between polarization and total intensity, is where we really will improve over previous data sets. And that's great because these channels are relatively clean for cosmology, because there's not so much contamination from extragalactic sources, because usually they're not polarized. And what's plotted here are these power spectra as function of multiples, so small scales on the right side. And the blue points here are from ACT DR4, so this slightly older data set. And then on top, there is just a fiducial spectrum plotted, and on top of that are just the error bars that we think we have at DR6. So they should scatter around, of course, and here they're just plotted exactly on the line, but it gives you an idea of the improvement that we'll get. And also this large patch of sky means that we can make very narrow bins in L, which is also nice if you want to look for certain features. All right, so this was about the power spectrum, but I said I won't talk too much about the power spectrum, so now we'll continue with the main topic, going beyond the power spectrum. And so I'll start with this summary of a recent result on CMB lensing, which is the first DR6 result. So it's not the main DR6 result yet, but it's the first time we're doing real science with this data set. This came out in 3 different papers in April. You can see the authors here, these 3 collaboration papers. So these papers focus on the gravitational lensing of the CMB. So what is gravitational lensing of the CMB? It's the notion that the primary CMB that's emitted at something like redshift of 1100 has to travel through all of the large structure to get to us, and along the way it gets slightly distorted. The nice thing about gravitational lensing as a probe of large structure is that it's sensitive to all matter. So not just baryonic matter, but both baryonic and dark matter, because you're really just probing gravity. So you can write down this kappa convergence thing that you hope to measure, which is just a measurement of the mass essentially along the lens. And then if we talk specifically about CMB lensing compared to galaxy weak lensing, which is another important cosmological probe, they are sort of complementary. The CMB, because you're looking at how the CMB at redshift of 1100 has been lensed, this means that you're sort of sensitive to all matter along between us and redshift 1100. And so that's illustrated here in this bottom panel, this lensing kernel, which tells you what redshifts are you sensitive to. For the CMB lensing case, in blue is extremely broad. And peaks somewhere around 2, but it's really quite broad compared to the galaxy lensing one in orange, which is more narrow and is you're sort of probing redshifts below 1. The dashed lines here are telling you what is the thing you're actually, what is the thing that's being lensed. So in this case, it's the CMB at 1100. In this case, it's objects around redshift 1. All right. So now I've skipped over many years of work where we actually use our raw data and we look for small anisotropic, statistically anisotropic effects that we can then use to reconstruct this lensing signal, this kappa map, which again tells you what is the matter along the line side. And these are the actual results. So this is a different way of plotting that I showed before, but this is basically the two patches that ACT-BR6 observed if you cut away the galaxy. In the background is just a map of dust as seen by Planck. So yeah, this is a wonderful map, essentially a map of the large scale structure along the line of sight, and it's an incredibly useful tool to study that, but also for cross correlations with other probes of large scale structure. This little gray rectangle here is then zoomed in here. It's transformed to form the lensing potential phi. It's basically the same thing. The purpose here is to show that it matches up very well with these colored contours, which is the CIB, cosmic infrared background, as seen from the Planck data. And then you expect that these two should correlate very well. And so this tells you that these are all signal-dominated ones. This is not noise we're seeing. We're actually seeing this matter. Okay, so if you want to do cosmology with this, you can do cross correlation, but you can also just look at this map and take the power spectrum of this map, and then you from theory, you expect it to look something like this. This is essentially just a matter power spectrum, but an integrated measure of that. This is the prediction you will get if you just take the lambda CEF parameters taken from the primary CMB, and you predict what should be the lensing power spectrum. Then I can overplot the data points that you got from taking the power spectrum on the previous map, and it seems to match up quite well. Again, this is using DR6, a subset of it actually, just our nighttime data and just in these two frequencies, not yet the 220 gigahertz data. It seems to be a good match, no statistical deviations. These gray bars are regions that we exclude for the main likelihood analysis, because either we're not entirely sure about our post-processing and modeling of instrumental effects, or we're not quite sure about the handling of extragalactic bodies. All right. Yeah, so what does this power spectrum, how to measure it, what kind of cosmology does this depend on? It essentially depends on these three parameters, omega m, sigma 8, and h naught. Just to remind you, sigma 8, I've said here, it's really the amplitude of the linear part of the matter power spectrum today. So essentially, and then defined at the scales of 8 megaparsecs. All right. Really though, what you're measuring is not sigma 8. If you just take this lensing power spectrum, you're measuring this combination of sigma 8 and omega m that people then call S8. So the combination is right there. And how you should think of that is in this two-dimensional plane of sigma 8 and omega m. You're measuring sort of this direction, as I indicated here with this arrow. But along these curved lines, you have no constraining powers. all right? So when I show results in this space, you should expect a sort of banana curve-like constraint, because you're really only probing where you are in this direction. Right. So then what is the goal of an analysis like this? I think the way I would like to think about this is we have this prediction from the primary CMB about the late-time universe. So we can fit, like I said here, step one, we fit these parameters to the primary CMB, and we get these derived parameters for the late-time universe, and then we compare this to this CMB lensing measurement, which really measures the late-time universe. And then we can see if things are consistent. So this is this contour that I alluded to, this banana-looking shape, and this is now the posterior derived from this CMB lensing power spectrum that we got. And then you can overplot the prediction from the primary CMB, and it matches up very well. So perhaps this was already not such a surprise, because the initial power spectrum also seemed to agree very well with the prediction. But so this is what we found. You may now wonder, what about sigma 8? Because this was essentially measuring this SA parameter. And the way to do that is to combine with something else. And in this case, we combine our data of the lensing power spectrum with BAO data. So large-scale structure survey, galaxy surveys measure this BAO feature. And just the measurement of this BAO feature tells you something about omega m and of the Hubble constant, but nothing about sigma 8. So that's illustrated by these dashed lines here. They are, there's no constraining power in the y direction, right? And then in red is this lensing banana-like shape. And here in black is just the prediction from the primary CMB again. But you can imagine if you combine these dashed lines with the red contours, you break this degeneracy, so that you can do that, and you end up with this. Again, showing consistency with the primary CMB. And by the way, also consistency with the Planck lensing. Okay, so that's my summary of our lensing results. Yeah, just to give a brief overview again, we're probing large-scale structure of this fairly wide redshift range. And the thing I didn't mention is that one selling point of CMB lensing is that you're really mostly sensitive to linear scales. So there's very little dependency on more complicated nonlinear modeling of small scales. We find that we're consistent with Planck, both at the lensing level, but also at the primary CMB level. If you look at this plot here, it's a plot of, at the top, the primary CMB constraints, and then here in red, the CMB lensing constraints, all on S8. And then in blue, constraints mostly from weak lensing and some galaxy clustering type of measurements. And there is this discrepancy, which remains after our result. Our result is mostly in line with is very much in line, I have to say, with the previous CMB results. The thing is, though, it tells you something about this discrepancy. It tells you that it's not seemingly a discrepancy between 1100, a redshift of 1100 and low redshift, but it's because we see that our lensing measurement of redshift 1, 2, 3 also seems to agree with 1100. So if you would rephrase this discrepancy, it would perhaps be something like either the very low redshifts are different, so redshift below 1, let's say, or there might be something different between the nonlinear or linear scales. So that's interesting thing that we'll have to answer in the future. All right, so the next topic I want to talk about is map-based analysis. So what do I mean with map-based analysis? I mean various things that you do with the maps themselves. So if you are looking for non-Gaussian signatures in the maps, if you're looking for this lensing signal that we talked about, if you want to perhaps remove this lensing signal, so de-lensing, or if you want to use our multi-frequency data to learn something about the different components of the microwave sky. All of this you generally would do in the map domain. You wouldn't work in the power spectrum domain, you would work in the map domain. And this is something we do, but we want to do more of, and this is difficult. One thing that makes all of these things difficult is that they all rely on what I here call optimal filters. So these are perhaps you know them as a Wiener filter or an inverse covariance filter. These are expensive operations in the map domain that you need to do if you want to do these sorts of analysis in an optimal manner. So let me give you a little bit more information on these filters. So this is sort of a joke that CMB cosmologists only know about Gaussian statistics, but it makes a lot of sense because our noise is fairly Gaussian, and the main signal that all of these analyses also have to deal with is the primary CMB, which to good approximation is also very Gaussian. So ultimately, most of these analyses all have to deal with this sort of statistics, and the statistics are very easy, right? If you're interested in the posterior here, signal conditional data, and you write that as a likelihood times a prior, your likelihood is a Gaussian likelihood because your noise is Gaussian. And your prior is also Gaussian because the CMB is Gaussian, or very close to Gaussian. Your posterior is also Gaussian, very basic stuff. But if you do this little exercise, you find that the maximum posterior value is given here, which is just the Wiener filter, which in more traditional statistics textbooks would be called the Wiener filter. So that Wiener filter is just the maximum posterior of this problem. The width of this posterior is then given by this quantity here. It's just a combination of S and N, which are the covariance of the signal and the covariance of the noise. All right, so this is a simple one-dimensional problem, but the same applies to our two-dimensional problem. So here, let me give you an example of what this then looks like. So here, I've taken a simulation of the Planck data set. I've zoomed in a little bit on a region, and the data itself is here at the top. This is at the left is the temperature, and on the right is one of the polarization components. So you see the polarization is very noisy. You see also this giant mask through the middle, that's the galaxy that is with mask. So then the row below that is showing you the Wiener filtered version of that data. And like I said, the Wiener filter is the maximum posterior value of the signal. So what does that do? In temperature, you have this very high signal to noise measurement. So the parts that you observe look almost the same. The parts that are masked sort of been filled in, because what is the maximum posterior value of that region? It's not quite zero because you know there is some correlation in the signal. So that correlated signal will sort of smoothly in-paint the unobserved regions. On the polarization side, you see that it additionally applies some sort of low-pass filter because you're sort of the very noisy regions are sort of smoothed away. Another way to think about a Wiener filter is that it's just filtering based on signal to noise. So eventually, all of the modes here usually are signal dominant. Okay, below that, I show a constrained realization. So essentially here I have a draw from this posterior, and this is ultimately all the same problem. So a draw from this posterior will in-paint this whole region with a likely realization of the CMB in both cases. Right? So if the Wiener filter is the maximum posterior, here I'm just drawing a sample from this. And then all the way at the bottom is this operation where I just filter the data by the inverse covariance, which is an operation that comes up a lot in the statistical estimators that we use. And so this is a filter where you suppress noisy data, but the noise can either be the instrumental noise, but it could also be the cosmic variance noise. So it's sort of a complicated filter that takes into account these two types of noise in a consistent way. So I want to, yeah, I've said already this, if you want to do this properly, this is a very expensive operation. And perhaps if you're familiar with this, you've probably encountered these type of filters, but just as a purely harmonic version. So you just assume that both of these covariances, signal and noise, are isotropic, so they're just given by a power spectrum. Then this operation is simple. But that's really not what it really ought to be, right? This neglects any anisotropic features in the noise, it neglects the sky mask and things like that. And doing it in this approximate way, sometimes fine, but it's suboptimal. You introduce sort of small biases, especially in polarization, and in some cases it does make your life harder because you're not doing everything in a consistent way. But doing the full thing usually requires an iterative solver. There's been a very extensive literature on doing this for CMB data sets, but we found that for ACT, this new data set, there's no good method yet, so we went out to do that. So to give you some idea of why this is difficult, I constructed this small one-dimensional problem where you can think of this as, let's just look at the sky, but we just take one ring of constant declination. So here at the x-axis, we have 0 to 360 degrees. And let's say the true signal is this blue line here. It is this correlated between pixels, sort of mimicking how the CMB signal is also correlated along scales. Let's say we have some data that we took from this in the data points here, and our data model is here on the left. We just have our signal in S gets hit by the beam of the instrument, like the point spread function. It then gets transformed to real space, because we started off in harmonic space, and then it gets masked, because let's say the galaxy was right here, all right? And we have some additive noise, which in this case is diagonal in real space. So it gives you these error bars. There's that slightly noisier here, and of course here there's no big one. Okay, so I hope this setup is clear. So again, if we now want to obtain the maximum posterior here, like I said before, we have to compute this Wiener filter, right? This Wiener filter, this is the same expression as I showed before, with these extra complications of this mask Fourier transform in the beam, but it's the same operation. So we want to evaluate this X Wiener filter thing here. But this is it's already for this small problem actually quite an expensive operation. And what you would do, or at least what we opt to do, is to use this conjugate gradient method. I'm sure many of you are familiar with. This is the most natural algorithm for solving some linear equation like this, where your matrix A is a positive definite or semi-positive definite matrix. And so really, you think of this as sort of a generalization of a steepest descent type of algorithm, which is a more general algorithm that looks for a minimum by just stepping down, knowing the gradient locally. Conjugate gradient is doing that, but in a slightly smarter way, because it works. It knows that these ellipses that are given by this matrix A correspond to a system that's described by a positive definite matrix. So, for example, for this two-dimensional problem, the conjugate gradient algorithm will just find the minimum always in 2 steps. It will do it if you have 2 dimensions, it'll find it in 2 steps. That's fun. That's nice. It's a smart algorithm. Of course, in our case, the number of dimensions is many millions, so we're not going to run this for many millions of steps. We hope that it finds some value that's good enough in a relatively small number of steps, a few tenths of steps. So let's run on our one-dimensional problem. Let's run this Wiener filter. It finds this green value, which again smoothly sort of interpolates the region that we've masked, and it also smooths some of the noisy regions a bit more, and it sure looks like maximum value, maximum posterior value of this problem. I also mentioned this drawing from this posterior. Things get a little bit more complicated, but the bottom line is, again, you can solve this with the same conjugate gradient approach. You just change the right-hand side of the system. So we can do that too, and here I've drawn some samples of the exterior. And this is a very useful thing for us to do, because unlike something like a metropolis hazing like of a Monte Carlo method, every one of these draws is truly independent from the other ones. The individual draws might be slightly expensive to compute, but in some cases that's a huge advantage if you don't have to run very long Monte Carlo chains to get a few independent samples. All right, so why is conjugate gradient tricky sometimes? It's because preconditioning is very important for conjugate gradient. So here I have that same linear equation AX equals B, but it's preconditioned by this M inverse matrix. And ideally you want this M inverse matrix to approach the inverse of A, make your problem simpler. But of course, if you knew the inverse of A, you wouldn't have to solve the problem. So there's some balance there. Here I plot for our simple problem this matrix, this preconditioned A matrix. And if I plot the eigenvalues of this matrix, you see this spectrum here with this sort of exponential drop. And this is why this problem is difficult. Conjugate gradient it roughly scales with the condition number, so the ratio between largest and smallest eigenvalue. In principle, it can deal with large condition numbers if there are some plateaus of equal or some sort of equal looking eigenvalues, but some drop off like this is not good. This is why even this small problem is actually quite tricky to solve for some. Okay, let's now get back to the CMB. Sorry, one more thing. That's what these small eigenvalues here, let's plot their corresponding eigenvectors. And perhaps unsurprisingly, they correspond exactly to these things that are masked, right? So these are the modes that were unobserved, so the solver has a lot of trouble finding these modes. Do you have a question?
Yeah, if you go to the previous plot, correct me if I'm wrong, but you want M inverse of A to be the identity matrix, right?
Ideally, yeah. Would be perfect if your eigenvalue spectrum just is all ones.
Yeah. So won't you be like wanting them to be one, because right now you have very small eigenvalues?
Yeah. So this is not a great situation, but
yeah.
So I've already preconditioned the system. My precondition has been a bit naive, perhaps. Like if I just plotted A, it was probably even more dramatic.
Okay.
But this, that's a good question. Okay. So yeah, these are the problematic modes. It's all due to the mask. All right, so now going back to the CMB, my little silly 1D example where these small eigen modes here correspond to these modes, sort of small eigenvalues correspond to these modes in the mask, seems to line up quite well with a slightly more realistic case where Planck, this is the Planck data from this wonderful paper here, where they also applied this mask and then did the same sort of analysis. You see exactly these problematic eigenvalues are the ones localized in the mask. Okay. Right. So it turns out to be very difficult to find a single precondition for the whole system that works. And this is annoying because now we can't do all these optimal things because we are unable to solve this system. So here I'm using a fairly involved precondition already, and I let it run for 60 conjugate gradient steps. And in this masked region here, it's clearly not finding, like I'm trying to get this constraint realization in here, it's not working. Here you can see the power spectrum as a function of steps going from purple to yellow. And you see, okay, at some scales it sort of has converged, but not here. And this will not converge if I run it for hundreds more steps, or even 1,000 steps. So really, at some point, probably you get in trouble with floating point errors and it will just stop working. So it's really sort of a no-go. Very unfortunate. So the idea now basically is we have a good preconditioner if the thing was not masked. Can we make sure we only use that preconditioner to the observed pixels, and then deal with the ones that were masked separately. And this work that I show here is inspired on this paper from 2017 that sort of did this. I will expand on it a bit, and then also eventually show, or we will eventually try to act, which is a whole different thing. Okay, so 2 slides where I get sort of in the weeds. We start up with this idea from fairly long ago, which is called deflation in preconditions. So we have identified some of these problematic eigenvalues, but we now make a matrix Z that corresponds to the eigenvectors of those eigenvalues. Once we have that, we can construct this projection operator R, and this R, in theory, would be an excellent preconditioner in the sense that because of this relationship here, which you could check by just plugging it in the above, using this R as a preconditioner would just put every input vector that's constructed out of these problematic eigenvalues, it would put it to 0. So that the conjugate gradient wouldn't see these modes anymore, essentially. They would be set to 0. The condition number would become much smaller, system much easier to solve. The idea then is you can split your desired solution X into 2 parts. This latter part is the part I just showed you. This deflated system has a nice eigenvalue spectrum and will converge rapidly. The first part here can be solved directly as long as this R matrix is not constructed out of many eigenvectors. This is a wonderful idea, but it doesn't work for us because we have actually many problematic eigenvectors. If this mask is large enough, we'll have 1 million problematic eigenvectors, right? So this first part, I will not be able to directly solve. The other thing is, it will be very hard to make a matrix R that does this, the projection perfectly. So these problematic eigenvalues that I claim were going to become 0 will probably become something small. And that's actually much worse, because I've turned something that was already small to something that's numerically close to 0, and that's horrible. So this really doesn't work, but it's a step in the right direction. The idea is then something people call 2-level preconditions. So now we use this deflation method, or at least its philosophy, but we combine it with another preconditioner, this MP inverse preconditioner here, that works well for the observed data. And we construct this sort of complicated expression, which you just have to think about in the following way. An input vector of the observed part of the sky will hit this expression, and it will only see the preconditioner that works well for the observed pixels. On the other hand, an input vector that's in the masked part of the sky will only see this this masked precondition, which is essentially a precondition that would work well for the masked part of the sky. And this, in theory, sets all the eigenvalues to 1. Like it moves, the large one gets put in. Again, this is only approximate, so it won't be perfect, but it does seem to work very well. Yeah, the thing, all the details that I'm skipping over now is how to evaluate something like this masked preconditioner. In practice, it means that you will either have another conjugate gradient solver that could be luckily at a lower resolution, or you implement what's called a multi-grid solver. In the sense that code eventually uses both of them. I won't go into details. What does a precondition like this do? It basically looks at the unobserved pixels, and it sort of predicts what should be in there, similar to how you would solve something like the heat equation or something. That's why something like multi-grid, if you're familiar with this, actually works very well. So anyway, that's the nitty-gritty part of it. Let me just show you now that it works. Here's a simple setup where I take a signal, I mask it, and I add some noise. And I want to draw some signal realization. So similar to how we did in this one-dimensional problem, I want to draw some of these realizations. So, so this is our input data. Now let us compare. At the top is two-level preconditioner, and at the bottom, more standard preconditioner. And I'm already showing the first step, because I didn't save the 0th step. And you can see already the first step is almost already solved the problem. And now as I go through the first 27 iterations, see that it's, if you focus on the top part now, it's sort of filling in everything. And at this point, we basically got the bulk of it, and now it's slowly fine-tuning it. While at the bottom here, even though the observed part of the problem is being solved, the unobserved part at step 27 is, you can probably not even see it here, is not even close to it. Of course, it's not exactly a fair comparison because this preconditioner is more expensive per step. But I would claim that this will not converge even after many hundreds of steps. So it is worth doing the more expensive. And in the end, you get something like this. I can draw another one, and if I flip between these two, or three, sorry, see that the middle part here, just the observed data, hardly changes, but the other part is truly, it seems like an independent constraint realization. And the same for the polarization. Okay. So with our optimal filtering, we're now at the step where we can do this with this two-level preconditioner. The other important thing is, what about this noise covariance matrix? And now I'll talk a little bit more about ACT. So, so ACT has to look through the atmosphere. The atmosphere in the microwave adds a lot of noise to our detectors. To get these maps of the sky, we jointly solve all of our data into a single map. This is a very expensive operation. We can only do it a limited amount of times. Resulting maps are unbiased, though. We don't apply any ad hoc filtering. The downside of that is that the noise becomes fairly complicated. So here is an illustration of what I'm talking about. So the noise spectrum here is a function of multiple. It's this extremely red spectrum. So the noise is very correlated. If I look at this map, that is an estimate of our noise by differencing two halves of the data, and we take the two-dimensional power spectrum of two different regions. You see they look completely different. This has to do with the way how the telescope scans over the sky, and it scans over different parts in different ways. So we have this very red correlated noise with directional correlations as well, and everything varies throughout the map. So it's a fairly complicated noise system. So together with Zach Atkins, a student at Princeton, we set out to find some sparse representation of this map-based noise, seeing if we could find something that is accurate enough and that is actually usable and not too expensive. And it turns out the thing we settled on is this wavelet-based model, basically based on the assumption that as a function of scale, so here I'm looking at the fine scales of the map of the noise, and here the large scales of the noise, you see that the morphology of this noise, which is of these maps, which in this case is showing the inverse covariance, changes a lot. So it is sort of a multi-scale problem where a wavelet-based method seems to be the natural thing to do. So that's what we do. I won't go into details here, but we built this wavelet-based noise model, which seems to, for our purposes, work very well, and it has already been used in this lensing result that I showed before. So here, just give you a slight taste of it. So here is the difference maps of the data. So this is an estimate of the true noise in Stokes I, so temperature and polarization. Again, showing you these two regions here as the two-dimensional power spectra. And then here's the same if you average over 10 draws of these SIMs, and you do see that it's picking up the right types of features in the mix. Okay, yeah, okay, I will go on. Okay, so this is the conclusion of this map-based part. With this too-low preconditioner, it allows us to optimally filter data sets, so really enabling a lot of these map-based analyses. One very important ingredient was modeling the noise, and so this recent work by us shows you that we can do this with these wavelet-based models. In an upcoming paper, we'll describe how to combine this new preconditioner and this ACT noise model into one and show that we can actually do this filtering. And then in the upcoming primordial non-Gaussianity analyses and upcoming lensing analyses, we will make use of all this machine. You can look at these two repositories for the methods themselves. Okay, and then for the last few minutes, I will just briefly advertise this data product that we have, which is about galaxy clusters and the thermal Zeldovich effect, which I'm sure many of you are familiar with. This idea that if a CMB photon hits the hot electrons present in a galaxy cluster, it gets its energy boosted slightly, which turns the CMB blackbody spectrum it moves it slightly towards higher energies. So if you then difference it with the average over the sky, galaxy clusters seem to get this characteristic spectral feature. An ACT is very well optimized to look for these types of clusters. Here, for example, if we just look at a cutout of the maps in the 3 different frequencies, you can see these 2 blue spots here. They're still blue at 150 gigahertz and at 220 gigahertz. They seem to have disappeared, and that aligns exactly with the type of shape you would expect. So this is how we could see all these galaxy clusters in the map. And you can make a catalog of all these the locations of all the clusters. This is showing the previous cluster catalog, DR5. For DR6, we will add something like 1,000 more. This will be a very useful product, I think. The thing I want to show here is yes. I don't know from the top of my head. I'll come back to it. It's okay. Yeah, no, it's a good question. Okay. Yeah, the other thing you can look at this TSE thermal synergic Zeldovich effect. It's not pretending that these are all discrete points, but just solving for the map that is consistent with that signal. So that's what we did in this work, where we combined our 3 frequency bands together with the Planck and WMAP data to form a map of the thermal Z signal. So you can think of this as a map of the integrated electron pressure along the line of sight, similar to how the lensing was an integrated measure of the mass. And this is a Planck-only version, and then this is the ACT version. So you can see that we really start to, because of our increased resolution, we get a lot more sensitive. And it's also much better at sort of removing dark spots like this from dusty sources, because we just have a better handle on point sources. Yeah, so this will be coming out soon, and this is my last slide. I think, although of course the CMB power spectrum remains our main probe and is very interesting on its own, I hope to have sort of inspired you and that there's lots more interesting things in our maps. I've not even mentioned all of these things. The other thing I talked about was the lensing result. We do seem to agree with this extrapolation from the very early universe. Then I talked about the map domain analyses and presented this new filtering approach that I think will enable a lot of these types of new methods and science. And then finally, you should look out for these upcoming maps of the TEC signal. I think will be a very useful product if you want to do cross correlations with larger structure or study cluster properties on it. Right, thank you. Yeah, so this problem gets worse and worse with signal to noise. So but I think this way of parameterizing the problem really separating the parts that is difficult, this mask part, will scale. In my experience, it is a very tricky system, and I'm sure you will have to tune things, but I'm hopeful, yes, that it is.
So you've already explained this, but I'm not sure I quite followed. Why is it necessary or optimal to infill the masked regions versus just using the data in the unmasked regions?
It's a good question. In some sense, if your solver doesn't solve those unobserved modes, right, or those regions on the sky, it means that you're not taking into account the mask and the correlations that the mask have induced in the data correctly. So it is, at that point, it is like you are just cutting out the data and taking a power spectrum of that, or something which we know is non-ideal because it will induce lots of mode coupling between the model. And so similar, if you don't let this problem converge, you would worry about things like that. And in general, you worry about non-converged conjugate gradient solvers because even though it's solving a linear equation, when it's not converged, there's no guarantee that things are linear. so if you want to do these things, you've got to do them sort of properly and make sure the whole system is solved. In my experience.
So I'll just ask a follow-up to that. So did Planck do that with the masked regions, and was there a similar solver?
For some analysis they did. For the lensing analysis they did. For the non-Gaussianity analysis they did not in the end. It means that for every analysis where you choose not to do it, you will have to show that you're not inducing a large suboptimality or any other biases. So that's they only use it for a few selectives, because even for Planck this is a tricky thing actually.
And did they use one of the simpler versions you were talking about?
Yeah, they used a method that was developed for WMAP. I wouldn't call it simple necessarily. It's also a lot of work went into that. It is a multi-grid solver, but it doesn't take into account this distinction between masked and unmasked. Like I said, there's been many papers written about this. It's an interesting subfield of CMB analysis.
Yeah, I thought what you said about the segmentation tension was really interesting. You said something about how like the tension could be in the linear versus non-linear. Could you just elaborate what, do you think it's like a data analysis thing that's going wrong in the non-linear fits, or is it just that we haven't accounted for some astrophysical thing that's affecting?
Yeah, I see what you mean. I mean, that would be somewhat speculative on my side to say what the Galaxy Lensing Group has not done. And I wouldn't even want to imply that it's a choice that they've made. It could be that there's truly something different in the physics, the nonlinear physics that we don't know about. What I would just like to say, it's just an observation, right? We we know our lensing result is sensitive to these certain redshifts, and it agrees with the primary CMB. Plus the observation that if in the lensing analysis if you look at the paper, there's one interesting plot where all of the nonlinear corrections in the likelihood are turned off. So we're just using linear physics, and it shifts the results by half a sigma or something. So it shows you that the dependency on nonlinear physics of the CMB lensing is nothing. So I just wanted to make that observation. At this redshift, we seem to agree, we're not sensitive to nonlinear physics. So that would imply that the solution could be in one of those two.
Are there any more questions in the room, or are there any online? Did not see any in the chat. All right. Okay, well, if not, let's thank our speaker again.